Hey everyone, hope you're doing well today. In this video, let's talk about simplifying exponential expressions. And of course, this is also known as simplifying exponential expressions. Let's jump right into some examples together. If you'd like to grab some paper and something to write with, let's go ahead and do some math together. For this first example, we have the quantity of 8 times p to the 5th power raised to the negative 2nd power. Now, before we even do any properties of exponents, just keep in mind that this 8 is raised to the 1st power and the p is raised to the 5th power. There are two bases in this expression. So we know there's two of these bases inside the parentheses, so this negative 2 on the outside as a power is going to be applied to both of these, okay? So what we can do is we can rewrite this as 8 to the 1st power, but that's going to be raised to the negative 2nd power. And we're going to multiply that by p to the 5th power, but that's going to be raised to the negative 2nd power as well. Using our power to a power property, we can go ahead and multiply these exponents together here. So we can rewrite or simplify this down to 8 to the negative 2 power, since 1 times negative 2 is negative 2. And for the second one over here, we have this 5 times negative 2 up here. So 5 times negative 2 is going to be negative 10. So we can rewrite this as p to the negative 10th power. Now, if the directions are to write this simplified expression not using any fraction bars, this would be 8 to the negative 2nd power times p to the negative 10th power. This is as far as you can go. However, if the directions are that you need to write your simplified expression using only positive exponents, keep in mind that this 8 to the negative 2nd power is equivalent to 1 over 8 to the positive 2 power, and p to the negative 10th power is going to be 1 over p to the positive 10th power. If you multiply these two together, 1 times 1 on top is going to be 1, and on the bottom, 8 squared is going to be 64, so we can rewrite this as 64 p to the positive 10th power. So using positive exponents, this would be the simplified expression. Let's try another one together. Here we have the quantity of 3 times r times s to the negative 3rd power, all raised to the negative 4th power. Just like in the last example, keep in mind that this is 3 to the 1st power and r to the 1st power, and we have s to the negative 3rd power, so there are 3 bases over here. This negative 4 is going to go ahead and be applied to all 3 of those bases, so it's going to go to this 3 to the 1st power, it's going to be applied to this r to the 1st power, and be applied to this s to the negative 3rd power. Rewriting this, we're going to have this 3 to the 1st power raised to the negative 4th power, and then we're going to have this r to the 1st power also raised to the negative 4th power, and then we're going to finally have this s to the negative 3rd power, and that's also raised to the negative 4th power. Now, using our power to a power property, we know that we can go ahead and multiply these powers together. So this 1 times negative 4 is going to be negative 4, so we can simplify this to 3 to the negative 4th power. And then for this next part, we have this 1 times negative 4, that's also going to be negative 4, so that is going to be r to the negative 4th power. And finally, we have this s to the negative 3rd power raised to the negative 4th power, and we can go ahead and multiply that negative 3 times negative 4, and that's going to be positive 12, so we'll have s to the positive 12th power. So writing this final expression using no fraction bars is just going to be 3 to the negative 4th power, r to the negative 4th power, s to the 12th power. Of course, they're all being multiplied together, but we don't have to write those dots. That multiplication is implied. Now, while that's writing the expression in most simplified form without using fraction bars, it does have negative exponents, so if you need to rewrite this using positive exponents, but you're allowed to use fraction bars, remember this 3 to the negative 4th power would be 1 over 3 to the positive 4th power. The r to the negative 4th power is the same thing as 1 over r to the positive 4th power, and the s to the 12th power, just keeping fractions here, is going to be s to the 12th power over 1, okay? And so you're going to notice that the s to the 12th power is going to stay on top because 1 times s to the 12th is just s to the 12th. And on the bottom there, we can multiply that 3 to the 4th power. That's going to be 81 if you multiply it out. And then r to the 4th power, I'm not going to go ahead and write that 1. So finally, we have this s to the positive 12th power over 81 times r to the 4th power. A key thing to remind you of is that when you have negative exponents, it doesn't really mean that there are negative values. It just means that you can rewrite that as the reciprocal as a positive exponent instead. So notice here we have that when it flips down, it becomes a positive 2 for the exponent. Here the negative 10 becomes a positive 10. Here the negative 4 exponent becomes positive 4 when you rewrite it. And this r to the negative 4th becomes r to the positive 4th as long as you reciprocate it and put it on the bottom. Here's a third example. We have the quantity of 6 times x to the 5th power times y to the negative 4th power, all raised to the negative 2nd power. So again, this 6 is raised to the 1st power. If you don't see an exponent, just give it a 1. and this -2 is going to be applied to all three of these bases. So it's going to go ahead to the 6 to the positive 1, x to the positive 5th, and this y to the -4th power. So going ahead and rewriting this, we have three bases here. So for the first part, we have 6 to the positive 1. So I'll go ahead and say 6 to the first power. That's going to be raised to the -2nd power. Next, we have this x to the 5th power, but that x to the 5th power is also going to be raised to the -2nd power, just like that. And then third, we have this y to the -4th power. So we're going to say, okay, that's y to the -4th power, and that's also going to get that -2 as an exponent. Now, going ahead, just like with the last two examples, if you'd like to try this on your own, go ahead and pause it, give it a go. This 1 times -2 is just going to be -2, so 6 to the -2nd power. Then for this next part here, we have this 5 to the -2nd, so a power to a power. We can multiply 5 times -2, and that's going to be -10. So we have x to the -10th power. And then third, finally, we have this -4 times -2, which is going to be +8, and so we can write y to the +8 power. So that was all the hard stuff we had to do. Now we can just go ahead and take away those multiplication symbols because they're implied if we don't write them. So we can write 6 to the -2 times x to the -10 times y to the +8th power. And this would be the most simplified version of this algebraic exponential expression using no fraction bars. Now, if you'd like to rewrite this using positive exponents only, this 6 to the -2 power is going to be 1 over 6 to the +2 power. This x to the -10th power is going to be 1 over this x to the +10th power. And for the y to the 8th power, that is going to stay on top because it's a positive exponent, and that's going to be just like that over 1. So now just going ahead and multiplying the numerators together, 1 times y to the 8th power is just going to stay as y to the 8th power. And in the denominator, 6 to the 2nd power we know is 36, and then x to the 10th power is just going to stay the same, and we can go ahead and drop that 1 because it doesn't change the value here. So using only positive exponents, but allowing a fraction bar, this would be the most simplified expression. For this fourth example, we have 4 times c to the 8th power times d to the -3rd power times 5 times c to the -5th power times d to the -1st power. So when you see these types of expressions where you know you're going to have to maybe combine some common pieces together, I recommend trying to just identify the pieces that are going to be the same or the bases that are common. So I'm going to go ahead and try to color code that for you right here. First, I think it's important to identify these coefficients because they can be multiplied together. Then we have these common bases of c that can be combined as well as these common bases of d. Now, while you might be able to combine these right away yourself, I'm just going to go ahead and rearrange this so it's a little bit more clear for those people that want to see that. Alright, so I know that might be a little bit extra, but just wanted to write that out so you can see the pieces that are going to be combined. So if we multiply this 4 times 5 together, we can just go ahead and write that new coefficient of 20 in front. Then when we go ahead and multiply this c to the +8th power times c to the -5th power, keep in mind that we can go ahead and take these exponents here, and we're going to go ahead and add them together. Okay, so 8 plus -5, that's the same thing as 8 minus 5. And so we're going to have c raised to the +3rd power. And then finally, for the base of d, we see that we have d to the -3rd power times d to the -1st power. So keep in mind that we can add those exponents together. So -3 plus -1 is -4. So we can go ahead and write this as d to the -4th power. Okay, so rewriting this as simplified as possible here, we're really going to have 20, and then we get rid of that dot there, and it's going to be times c to the 3rd power, and then times d to the -4th power. So using no fraction bars, this would be the most simplified expression, even though we have a negative exponent in there. Now, just say you wanted to rewrite this using no negative exponents and you wanted to use a fraction bar, then this 20 is the same thing as 20 over 1. And this c to the 3rd power, that's going to be equivalent to c to the 3rd power over 1. And then finally, for this last part, this d to the -4th power, if you want to write that using a positive exponent, that's going to be 1 over d to the +4th power. Okay, if we go ahead and multiply these now, on top we're going to notice that we're going to have this 20c to the 3rd power in the numerator. Okay, and in the denominator we're going to have this d to the 4th power. So that's going to stay down there. So if you wanted to rewrite this expression using no negative exponents and fraction bars are okay, then this would be it. Here's a fifth example. We have the quantity of x to the 2nd power times y to the 3rd power multiplied by the quantity of x to the 5th power times y to the 4th power, all raised to the -3rd power. Technically, this first group of parentheses has an invisible 1 over here, so this 1 gets applied to everything inside, but nothing is really going to happen there, so we can go ahead and ignore it. But this -3 in the second one is going to be applied to this x to the 5th power and to this y to the positive 4th power. Another thing to note here is that we should probably group and identify which bases can be combined. That being said, here we have this base of x that will eventually combine later, as well as this base of y. Let's go ahead and take care of the parentheses first. So I know I said a little bit earlier that this 1 really wasn't going to do anything, so I'm just going to go ahead and simplify this. I'm not going to show the multiplying of the exponents here. This 1 times 2, I'm just going to go ahead and rewrite that. That's going to be x to the positive 2 power. And then this y to the 3rd times, raised to the 1st power rather, is going to just be y to the positive 3rd power. Next, after that, this x to the 5th power raised to the negative 3rd power, I'm just going to go ahead and multiply 5 times -3. That's going to be x to the negative 15th power. And then finally, this y to the 4th power raised to the negative 3rd power. 4 times -3 is -12, so we're going to have y to the negative 12th power. So hopefully this looks a little bit less intimidating just because we don't have parentheses anymore, but now we can go ahead and rearrange and multiply the same bases together and add their exponents. Now, just like earlier, I'm going to rearrange these one more time to hopefully make it a little bit more clear. So here we go. So we have our common bases next to each other. Those are the ones that can be combined. And keep in mind that when you multiply these with common bases, all we're going to do is go ahead and add their exponents together. So this 2 plus -15, that's going to be the shortcut there. We can go ahead and rewrite that as x to the, what is that, negative 13th power, right? 2 minus 15. Same thing as 15 minus 2, just make it negative. And then for this next part here, we have this y to the 3rd power times y to the negative 12th power. If we add 3 plus this negative 12, or through 3 minus 12, that's going to be -9. So we're going to have y to the negative 9th power. Okay, getting rid of that multiplication symbol, we can go ahead and simplify this down and say this is going to be x to the negative 13th power times y to the negative 9th power. So this right here would be our most simplified expression, not using a fraction bar. Whoops, I forgot to write the little plus sign up here, but just keep in mind that's what we did when we multiplied this together. We added those exponents together. If we wanted to rewrite this using positive exponents only, this x to the negative 13th power is equivalent to 1 over x to the positive 13th power, and this y to the negative 9th power is equivalent to 1 over y to the positive 9th power. Multiplying those 1's together on top, we're just going to get 1, and in the denominator we can just go ahead and squish those together because they're multiplied, and that's going to be x to the 13th power times y to the positive 9th power, and this right here would be the same value, just using fraction bars and positive exponents instead. Here's another one. In this problem, we have the quantity of n to the 5th power times m to the 0th power times x to the negative 5th power, all raised to the 2nd power, times negative y times x to the positive 2nd power. Now, if you'd like to pause and try this on your own, give it a go. Otherwise, let's go over it together. So first I noticed that there are no coefficients, which means they're just 1's hidden everywhere. And let's go ahead and see what types of letters we have. This m is all alone, so that's not going to be combined with anything at any point. This n also appears to be alone, so that's not going to be combined with any others as well. However, these bases of x will eventually be combined at some point. And finally, this lonely y won't be combined with anything as well, and it has an invisible exponent of 1. Now, a couple key things to note right from the beginning is that we have this m to the 0th power over here, and that anything raised to the 0th power is just going to equal 1, so that's going to be nice and get rid of this m right from the beginning. After that, we want to take a look at this 2 here, and notice that 2 is going to belong to all 3 bases, but I'm just going to give it to this n to the 5th power and this x to the negative 5th power, just because we know that m to the 0th power is going to go away right at the start. So let's go ahead and clean this up a little bit. If we go ahead and take this n to the 5th power and raise that to the 2nd power, again, we're going to multiply those exponents together. And so 5 times 2 is going to be 10, and we're going to have n to the positive 10th power. And the next part, again, we're skipping that m to the 0th power. This x to the negative 5th power raised to the 2nd power, negative 5 times this positive 2 is going to be negative 10. So we're going to be multiplying this by x to the negative 10th power, just like this. Okay. Following that, I'm just going to go ahead and rewrite the rest of this expression. So we just have this negative y to the 1st power, negative y raised to the 1st power, and we're also multiplying this by this x to the positive 2nd power. Now, just to make sure you understand what this negative means, there's really just going to be this -1 as a coefficient in front of this y, but we don't write the 1, it's just implied. So if you see that negative, just keep in mind that there's a coefficient of -1. Now I'm going to go ahead and rearrange this so we have our coefficient in front and our common bases in order alphabetically. Alright, so hopefully it makes sense that I've just rearranged this a little bit and it's a little bit more clear what we can combine and what we can't combine. So in the beginning here, I'm just going to write the negative. I'm going to drop the 1 now. We know it's there. I just wanted to write it so that we knew that was in front. Then we have this x to the -10th power being multiplied by x to the 2nd power. And keep in mind when we are multiplying them, the shortcut is we can add those exponents. So if we go ahead and add -10 plus 2, that's going to be -8. So that's going to be x to the -8th power here. And then finally we have this y to the 1st power, but I'm going to go ahead and drop that +1 and just write y. Now, dropping those multiplication symbols, here we can finally write that we have a final expression of -n raised to the 10th power, and then squish it all together. We're going to say this is going to be x to the -8th power, and then we have a y at the very end here. So using no fraction bars, this would be our most simplified expression. And if we did want to write it using positive exponents only, this negative is going to stay in front. We're going to have this n to the +10th, and that's going to be over 1. Keep in mind the negative in front doesn't mean it's a negative exponent, so that's not flipping at all. This x to the -8th power is going to be 1 over x to the +8th power. And for this y, that's really going to be y to the +1st power over 1, just like that. And then finally, we can go ahead and multiply together and say this is going to be -n to the 10th power times y for our numerator. And for our denominator, the only thing that had a negative exponent was that x to the -8th. So when we move it down, that's going to be x to the +8th. So this right here would be our most simplified expression. Let's try this one. We have y to the -4th power times x to the 4th power times y to the -2nd power times the quantity of -x to the 3rd power times y to the 3rd power, all raised to the 2nd power. Now, a couple key things to note here is that we do have an invisible 1 as a coefficient in front of this x to the 3rd power. And then we also want to notice that this 2 on the outside of this parentheses is going to be applied to really 3 bases here. It's going to be applied to this -1 that was invisible. That's also raised to the 1st power. And then with this 2 is also going to be applied to this x to the 3rd power. And it's going to be applied to this y to the 3rd power. So a lot of people miss the fact that that -1 is going to be raised to the +2nd power as well. So I just wanted to take note of that. After that, I just want to go ahead and make sure we understand where all the common bases are going to be. So we do have this coefficient of -1, keep that in mind. Then we have our common bases of x and our common bases of y. To begin, I'm just going to go ahead and rewrite this expression so that we get rid of the parentheses. So I'm going to just copy this y to the -4th power multiplied by this x to the +4th power. I'm just going to put some dots in to keep things a little bit more organized as well. This is going to be y to the -2nd power. And now what's going to be happening here? Well, we have -1 raised to the 2nd power. So -1 squared is going to be a +1. So -1 times -1 is a +1. And then we have this x to the +3rd power raised to the 2nd power. So multiplying 3 times 2, that's going to be 6. That's going to be x to the +6th power. And then finally, we have this y to the 3rd power, but we're going to square that. So 3 times 2 is going to be 6. So that's going to be y to the +6th power. Okay, so if you need to pause and think about that for a moment, we get this +1 because the -1 squared is +1, and we just multiply the power to a power property. 3 times 2 is 6, and 3 times 2 is 6 for those exponents. Next, feel free to skip this step, but I'm going to go ahead and rearrange this entire expression so that we have our coefficient first, and then our alphabetically organized variables and bases from left to right. Alrighty, so we have our 1 in front, then we have our x's, and then we have our y's. And now we get to go ahead and just simplify this by adding some powers together. We're really multiplying them, but I mean, we're adding their exponents as the shortcut, right? So we have this 1 in front, and then we multiply this x to the 4th times x to the 6th. That's really just 10 of these x's being multiplied together, so that's why we add those. So we're going to say that's going to be times x to the +10th power. And then for the y's, we can multiply these all together because they have common bases of y. And when we do that, we're going to add their exponents. So -4 plus -2, that's going to be -6. And then -6 Ooh, adding this positive 6 is going to be 0, so this is going to end up being multiplied by y to the 0th power. Okay, so keep in mind, if we have something raised to the 0th power, like here, y to the 0th power, that's just going to equal 1. Anything raised to the 0th power is going to equal 1. So what can we rewrite this as? We're going to drop that 1 in front, and it looks like we actually just have a simplified expression of x to the positive 10th power. Again, that 1 doesn't need to be written, and all the y terms, or all the y bases rather, canceled out. And since it has a positive exponent, then this is how you would write it no matter what for our final simplified expression. Let's try one last one together. We have the quantity of a to the negative 5th power times b to the 8th power times c to the negative 12th power times the quantity of a to the 7th power times b to the negative 3rd power times c to the positive 7th power. We don't have to worry about the power of a power property. There is an invisible one up here and an invisible one here, but if we go ahead and apply that to every base, nothing's going to happen because of the identity property. Everything times 1 is going to stay the same. So just letting you know that technically we do have to do it, but we don't really need to write it when there is no power there. We just know it's implied as 1. Now let's go ahead and identify our common bases so we know which ones need to be put together. So we have our common base of A, our common base of B, and our common base of C. Now these powers of 1 are going to be applied to each of these bases, but nothing's going to happen, so I'm just going to go ahead and drop the parentheses for this first one, and I'm going to do the same thing for the second one as well. Again, this is totally unnecessary. I just want to make it very clear because some people may find some benefit to just seeing that like it's not that some problems do it and some problems don't. They all technically do it. We just don't have to write the 1. Now I'm going to go ahead and simplify this using just dots in between everything, get rid of those parentheses, and I'm also going to reorganize it as well. So let's go ahead and do that together. Alrighty, so I kind of did two things at once. I got rid of the parentheses and I reorganized. Remember, we can multiply in any order here, so that works out quite well. And we don't really have to deal with any coefficients. There are invisible ones everywhere, so again, we're not writing those either, just because 1 times anything is anything. So there's a lot of hidden things going on. Just want to make sure that is clear. So next we can go ahead and multiply these parts that have common bases. So if we're going to multiply this a to the negative 5th times a to the positive 7th power, keep in mind we're going to go ahead and add these exponents together rather. We're multiplying the powers, but we add their exponents as a shortcut. Negative 5 plus 7 is going to be a positive 2. So we're going to have a raised to the positive 2 power. Following that, we're going to have this b to the positive 8th power being multiplied by b to the negative 3rd power. If that's the case, we have this positive 8 being added to this negative 3 as our shortcut. 8 plus negative 3 is really just 8 minus 3. So that's going to be b to the positive 5th power. And then finally, we have these c's. So the c to the negative 12th power times c to the 7th power, those can be combined. If we go ahead and just add this negative 12 and this positive 7 together, negative 12 plus 7 is going to be a negative 5. So we're going to go ahead and rewrite this final part as c to the negative 5th power. Now, if we want to just squish everything together and rewrite this so it's all cleaned up and as written as short as possible, we have a to the 2nd power times b to the 5th power times c to the negative 5th power. So this right here would be our most simplified expression using no fraction bars. And let's just say you did want to rewrite this expression using only positive exponents, then this one stays the same, this a to the 2nd power. This b to the 5th power is also going to stay the same, so we have b to the positive 5, that's going to be over 1. And for the only one that's going to be moving to become a positive exponent is a c to the negative 5th power. It's going to be 1 over c to the positive 5th power. So finally, rewriting this, we can squish it all together. The tops being multiplied is going to be a squared times b to the positive 5th power. So we have our positive exponents up here. And in the denominator, the c to the 5th power is now positive, so we can go ahead and write that down there. And everything's positive now. So this would be another version of the most simplified expression, but using positive exponents instead. And there you have 8 different examples of simplifying exponential expressions that really just deal with using the product property of exponents and the power of a power property. I didn't do any with fraction bars in this video, but I will in another one, so look out for that when it does come out. I know these problems can be a little bit tricky, but hopefully the different colors and the different steps help make it a little bit easier to understand. And as always, keep up the amazing work that you're already doing, and don't forget to simplify.